The night sky is like a time machine. The further we look in the universe, the further back in time we go. What we see in the night sky is only a small percentage of the universe's content. Most of it is dark matter and dark energy. We know it exists, but the universe is currently deceiving us. Thanks to advances in technology and engineering, telescopes and other sensors can now obtain clearer images from orbit without being tied to a frequently polluted, hazy atmosphere. In the 1960s, satellites began exploring the universe around us, seeing beyond visible light, ultraviolet, infrared, the first signs, and even gamma rays. The universe itself is evolving and constantly expanding, with an understanding of its beginning, structure, evolution, and future. In the last 20 years of the 20th century, the United States and other nations began developing more significant research programs using larger and more complex space-based telescopes. For hundreds of thousands of years, people thought the universe was a static place. If you go out at night and look at the sky, you see that many things haven't changed. For a long time, the universe was seen as very stable, but we know that this is not true. The universe is an extremely dynamic place, and something is happening every moment, every second. Somewhere in the universe, a star explodes in a massive supernova, and our goal is to go and find it, to build instruments that can detect these unpredictable events. The cosmic background, or COBE satellite, began to crystallize the big picture of the universe by mapping microwave background radiation from the early universe. A map that continues this process has created the most detailed portrait of the universe's infancy. Because the light took more than 13 billion years to reach us, we now see what the universe looked like 13 billion years ago. It's a fossil remnant of what the early universe was like. And just as fossils are used to study the past, we use this light to study what the universe was like near its beginning. You can see blue dots and red dots there. These correspond to hotter and colder images of the sky. It's an image with hot and cold dot patterns. This is truly a flash from after the Big Bang. On a deeper and longer term level, the picture of the universe that we can put together is relatively simple. And this astonishing consistency, where the pieces fit together, is a striking confirmation of many years of cosmology studies. It was just constructed, and here we are in some ways, recognizing the universe as if it were our own backyard. We begin to recognize it as Lisa's Planck spacecraft joined the fleet and expanded its observations. Together, these mapped vast regions across multiple wavelengths, allowing astronomers to determine the size, shape, and age of the known universe. Just 370,000 years after the universe began with the Big Bang, all that existed was a hot, plasma-like mass resembling a candle flame. Protons and electrons, seen as red and green balls, scattered light bouncing around. Light particles called photons, shown in blue, couldn't travel far without colliding with an electron. As the universe cooled, protons and electrons paired up to form hydrogen atoms, and light began to travel freely. It traveled freely throughout the Dark Ages, before stars formed, and then again since the formation of the first stars. As the universe expanded, photons lost energy and changed color. They passed by galaxy clusters. The path of a photon is slightly bent by the gravity of the clusters. Now and then, as an electron passes through a cluster, it collides with some of those green ball photons, changing their paths. As more matter passes, more small wobbles occur due to gravity and mass. Before reaching the Planck detectors, they traveled for 13.8 billion years, traversing the entire universe that had gloriously died, leaving the information they gathered on our instruments, and enabling us to create this beautiful map of the universe. Various satellite telescopes are designed for use across a wide range of wavelengths, In the electromagnetic spectrum, from near and far infrared light to visible and ultraviolet frequencies, from the first to the wedge and cosmic ray detectors, each capable of revealing unique aspects of the structure of stars, nebulae, galaxies, exotic quasars, and black holes. But in the public eye, the poster star of the last generation will undoubtedly be the Hubble Space Telescope. During its 25-year lifespan, it has produced some of the most astonishing images of the cosmos by going back in time through visible and infrared light. Another advantage of Hubble is its longevity thanks to various maintenance tasks. This allows it to study objects for a long time and obtain some amazing results. Newborn stars eject streams of matter into the star-forming region around them, each known as a Hubble object. These supersonic jets can be seen changing over very short time intervals. When you see a single image from Hubble, you naturally see it in many different ways. You can interpret this, but if you change your perspective a little, the main thing to consider here is the fact that Hubble has existed for so long. That's what should really be thought about. The Horsehead Nebula, with its silhouette of glowing gas in the constellation, is a good example of this. By revealing the dark secrets of infrared, we can see right into its center. The Spitzer telescope is one of NASA's great observatories. It's an infrared telescope, meaning it sees inside the dust in space, and by seeing inside the dust, we can pinpoint the star nests where stars are being born. We've been using it for about 10 years, which is about 3,600 days. We have 5,000 published articles. This means that every day a new article is published explaining new results and new discoveries based on Spitzer data, which is absolutely amazing for me. The speeder has made many amazing discoveries in our solar system and beyond, helping us to pinpoint some of the most distant galaxies in the universe. And Spitzer's ultra-high resolution map of the Milky Way has significantly improved our understanding of the structure of our own galaxy. Japan and the USS Shell have launched their own infrared telescopes in various infrared wavelengths, especially European ones, each focusing on major star-forming regions. We have new things to understand. We are really happy to be working on this because we are taking a new step toward understanding massive star formation. Therefore, there is the idea that Herschel, for example, can reveal this highly embedded star population that forms the gas and dust cocoon invisible at optical wavelengths. Therefore, we need Herschel to detect all this very young star population. The next major space-based infrared telescope is the James Telescope, which is nearing the completion of its tests and is preparing for launch in 2018. It will have a 6.5 meter primary mirror, almost 3 times larger than Hubble's. However, ground-based telescopes also work in the infrared spectrum, so there is a great complementarity between space and Earth. From space, you can characterize the images we see with Hubble images much better. If you take this light with your telescopes and look at the spectrum, you can find the redshift for distant galaxies, or you can do infrared observations that Hubble hasn't been able to do for a long time and see how these objects look in the infrared. They investigated star-forming nebulae left over from supernovae that exploded together and witnessed the birth of stars. For astronomers and cosmologists in the electromagnetic spectrum, another observational tool is the X-ray band. Every galaxy, like the Milky Way, has a massive black hole at its center, and as matter like dust and gas from this galaxy falls onto this central black hole, it emits radiation, which we can observe. In other words, if we look at the sky with visible light, we see stars. If we look at the sky with X-rays, we see black holes. You can observe the first rays coming from very distant objects and thus investigate their cosmic structure. Then, by observing galaxies and the active black holes at their centers over very long distances, you can investigate the distribution of matter in the universe. This is very important in cosmology for gaining information about the origin and evolution of our universe. X-rays are absorbed by our atmosphere. Therefore, the first scattering detectors must be placed either in balloons at high altitudes or in orbit. NASA's flagship X-ray telescope and one of its major observatories is Chandra. If you want to find black holes, you must use an X-ray telescope. It usually has a bright central galaxy, often an active galaxy or quasars. So a supermassive black hole is located in the center of a large galaxy. Because of its formation, when it comes to that, a lot of material tends to fall out. So you get the biggest galaxy in the middle. So you see the power of an observatory, a state-of-the-art telescope like Chandra, an observatory and scientific instruments with these spectroscopic imaging capabilities. Maybe you can't even do the things you plan to do because you didn't know about them back then. Much of the science done with Chandra falls into this category. The latest launched telescope, NuSTAR, has the ability to focus on X-rays for a much sharper image. One of Luster's main scientific goals is to make a complete count of black holes in the universe. X-rays have also revealed the explosive processes of novae, which are only seen at these wavelengths. The International Gamma Ray Astrophysics Laboratory, which studies cosmic evolution, has Integral, which has revealed new gamma ray sources and studies gamma ray frequencies. Integral is important because it is one of the few satellites that look at gamma rays. Also, together with other satellites and observatories around the world, we can get a complete picture of how these stars evolve, but without Integral, you would be missing a big piece of the puzzle that we have created. We want to know how they produce elements. These are objects that scatter different kinds of materials into the universe and travel curiously into space. We are made up of all these elements produced by supernovae. Therefore, it is important for us to know where and how life originated. Gamma rays are at the very top of the electromagnetic spectrum. They are the most energetic and powerful photons coming from black holes, exploding stars, and even our own star, the Sun. The Fermi Gamma Ray Space Telescope, originally named GLASS, observes the entire sky with high-energy gamma rays every 3 hours, creating the most detailed map of the universe known to date in these energies. When it detects a new gamma ray burst, it works with swift sense of direction, so it can quickly spin around the sky, and an X-ray telescope and an optical ultraviolet telescope can be directed to the possible location of the gamma ray burst. GLASS is primarily dedicated to seeing in a new energy range that Swift designed to take from the upper end of the energy range and move it to much higher energies. And the higher you go in the energy, the stranger and more exotic things you see, and Swift is a small, agile satellite that points here and there. It's like that, but it doesn't scan the whole sky. Beryl points to objects. GLASS looks at high gamma ray sky. It always examines the whole sky. So when we see something interesting with GLASS, we can ask Swift to look with its other telescopes and get additional information. We don't know what will happen in the next 10 years. We hope Swift will still give us exciting data, but one thing we know is that the pair's pure nature results in interesting new data. Swift was built for this, to study unpredictable and unexpected new events, and these are inevitable. There is another type of radiation being studied in orbit, cosmic rays. The 8-ton cosmic ray particle detector, called the Alpha Magnetic Spectrometer, or EX instrument, is attached to the International Space Station. Cosmic rays consist of protons, alpha particles, atomic nuclei of heavier elements, electrons, their antimatter counterparts, positrons and gamma rays. Studying these particles can answer some fundamental questions such as the unexplained absence of antimatter and the nature of dark matter in the universe. The calibration of the positron is very important because when dark matter collides with other dark matter, a positron is now produced. Therefore, now the characteristics of positions tell you what the origin of dark matter is. About 80% of the matter in the universe is invisible to telescopes. This dark matter does not reflect, absorb, or emit light, but it interacts with matter through a gravitational effect that can be seen in the orbital velocities of stars around galaxies and the movements of galaxy clusters. Yet, despite decades of effort, no one knows what this dark matter actually is. This image shows galaxies composed of gas stars and dark matter colliding to form large-scale filaments in the universe and create a snapshot of the cosmic web. Dark matter is believed to provide the framework for this web. Galaxy clusters are the largest gravitationally bound structures in the universe. It is also believed that the expansion of the universe initially slowed after the Big Bang, but then shifted gears and began to accelerate. Jesus, a space telescope with a launch date set for 2020, is under construction, hoping to map the effects of dark matter and dark energy on the universe. I am working on it, a mission to map the universe, and for this we can map the structures of dark matter and dark energy. We are building an extremely sensitive telescope from which we can derive its properties. Understanding dark energy will allow us to understand the future of the universe. The interesting thing is that we are having more and more dark energy. Why? Because our universe is expanding, and in our expanding universe we are getting more dark energy. Ordinary matter and dark matter are not expanding, they are diluting. Therefore, the ratio of dark energy to normal matter is increasing over time. As the universe expands more, we get more volume in our universe, we get more space, we get more dark energy. The leading particle physics model for dark matter is called weakly interacting massive particles, also known as cranes. These fly through the universe without colliding with anything or each other. The idea of two films coming together and creating gamma rays is like two bullets colliding head-on in a crossfire. But when you go to the area around a supermassive black hole, you expect the density to be much higher. Therefore, the probability of sudden halos is much higher. This is how it can be detected with a gamma ray telescope. In the theoretical process, the computer simulation of Schnitz shows dark matter particles around a rotating giant black hole. All the movement is near the event horizon of the black hole, beyond which nothing goes. The black hole's rotation occurs in a flattened region called the ergosphere, at the boundary where nothing can escape. Within the ergosphere, the black hole's rotation drags space-time along with it, forcing everything to move in the same direction at almost the speed of light. Condensed, fast-moving dark matter particles collide and create gamma rays. However, only a portion of this high-energy light can escape the black hole. In this case, the black hole is rotating towards us from the left, giving us the glow of its high-energy rays. The simulation tells astronomers that this is an astrophysically interesting signal that they will be able to detect as gamma ray telescopes develop, and they believe it will be definitive proof. In my opinion, the coming together of dark matter and black holes, two of the most difficult things in the universe to explain, is quite poetic. Future missions will see a gravitational wave observatory to study gravitational waves and test Einstein's general theory of relativity. The Athena mission will map hot gas structures and search for supermassive black holes, launching in 2028. The Sloan Digital Sky Survey, the most ambitious astronomical survey to date, will create a three-dimensional map of approximately 1 million galaxies and quasars. The recently upgraded and enlarged Large Hadron Collider is one of the instruments searching for weakly interacting, massive particles and other exotic particles that could help explain the structure of the cosmos. Then perhaps scientists, astronomers and engineers can turn their attention to other mysterious theories brought about by particle physics, such as multiple dimensions, entire universes beyond their own, and what lies beyond the event horizon. These will become new frontiers in time,